everyone! Today I'll show you some important components of NMT. I'll then go on to show the difference between studying ionic activity using NMT as opposed to traditional microsensors that are based on microelectrode technology. This here is the NMT system produced by YoungerUSA. It is made up of three main components: the signal acquisition system, the motion control system, and the data analysis system. Since NMT is a very sensitive system and can pick up signals from electronics such as cell phones and televisions, the Faraday cage is needed to block out all of this electronic noise, which could result in false readings. Now let's look at the basic setup for testing. A petri dish is placed on the microscope stage to hold your sample in place. Here we will look at an Arabidopsis seedling. The NMT sensor is used to measure a specific ion or molecule. This sensor is controlled by a 3D manipulator which can be moved in the X, Y, and Z axes. The 3D manipulator also plays a crucial role in the flux measurement, which I'll cover in another video. NMT uses a reference electrode to make a complete circuit which collects electronic signals from the NMT sensors. To collect the image information, NMT has an image acquisition system. This allows scientists to look at the relative positions between the NMT sensor and the live sample they are studying. Since the tip of the NMT sensor has a diameter as small as 2 microns, NMT is an ideal technology to study specific parts of live samples in the exact place that you would like to study them. It is important to remember that in order to measure ionic and molecular fluxes, samples need to be in a liquid media environment. You may be wondering if this affects the accuracy of a sample that isn't naturally found in a liquid environment. Well, the media added should reflect as closely as possible the sample's real-life environment. So even though the Arabidopsis seedling isn't in soil, it will still behave as closely as it would in its natural soil environment. Now, the light source and microscope collect the information of the image while measurements are taken. Now that we've gone over the basics of NMT, let's take a look at traditional microsensors based on the microelectrode technology. These technologies use electrodes that are often larger than the test sample, which leads to a much lower spatial resolution than NMT. Have you been trying to get information on the ionic or molecular activity happening around your samples? For example, let's say you have spent a lot of time trying to prove that hydrogen ions act a certain way in Arabidopsis. You have tried using a traditional hydrogen microsensor but ended up with results like this, a straight line that essentially tells you nothing. Now, assuming these hydrogen ions really do act the way you think they do, NMT can give you the important results you have been missing with the traditional hydrogen microsensor. NMT detects both magnitude and direction of the hydrogen ions around the Arabidopsis seedling, showing much more than just the static ionic concentration that is found with traditional technologies. The results are obvious. If you are looking for a technology that can study living samples non-invasively and in real time, NMT is your best choice. We recommend this technology because it is able to pick up more signals than other technologies. With NMT, your new discoveries are just around the corner. If you are interested to see more examples or real-world applications of NMT, please subscribe or visit our website. Thank you for watching. See you later.